Hi, welcome to my lab 3, which is about the magnetic field of a bar magnet. So the purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet, and then to compare the measurements to the distance dependent predicted by the equations for the on and off axis magnetic field. And we're going to incorporate these calculations into the specific law to find a magnetic moment of the bar magnet. And then we're going to create a computational model of the experiment using Python glow script code, um, all to just analyze the discrepancies between the values and discuss possible sources of error. So the fundamental physics principles used include the Biot-Savart law. This demonstrates the connection between the magnetic field at a specific coordinate and also distance. So the arrow kind of points to that one, and then we're also, in order to linearize our data, we're also going to take the natural log of it so that it appears in a clear order for our graph. And then we're also going to use the distance dependence formula, and then we're going to solve for mu. Just a preview of the results, I got mu equals 1.7 and n equals negative 3.4. The initial conditions, the systems equal the bar magnets and the surroundings equals everything else in Earth. The initial conditions include like the magnet and our marble device, and then with the magnetic field reader application downloaded on it. And I'll talk about that in a little bit. So the model description, so we're going to place a ruler from east to west axis of a bar magnet and then place the hold perpendicular to the meter stick and move it up and down on the perp axis. Then we rotate the phone 90 degrees and do the same motion. And that's to pinpoint the location of the magnetometer on the phone. And then on and off axis, the measurements were taken and recorded. And then I'll show you the Excel file on the next slide. But basically, this procedure is kind of just to pinpoint the location of the magnetometer to get more specific data. And then, as I said before, this was also done then on the perp axis as well, and that distance was recorded. So this is the data that I recorded. As you can see, we have 3 trials for each of the R20, R70, all the way up to R22. And then here is our perp axis data. These values will become very important because this linearized data is what we used as our n value and our b net value, and that's how I calculated k. So we record, like I said, we recorded the distance, and then we used a natural log normalization to get a very specific linear equation, and it relates to the ln(bx) equation. Then I solved for k using that equation with the y-intercept, and I got k equals 1.17 times 10 to the negative 7. And then I was able to use that to calculate the magnetic dipole moment. Then we recorded the perp axis distance that gave us the 100 UT. And we recorded the XYZ components as discussed in the experiment details. This is the computational model of just the magnetic field presence. As you can see, this is kind of creating the magnetic at the origin, whereas this is actually visualizing the magnetic field on the 45 degrees off axis. And then we were able to calculate the actual distance d with our vector. So just the conclusion and possible sources of error. So as you can see, this is the calculated, and this was the real version just screenshotted from the Excel sheet that I showed you with my specific data. The magnitude of the distance was 2.1283 times 10 to the negative 5. So possible sources of error that can really identify the discrepancy in the magnitude of the to computational model and the experiment is that my procedure in identifying the phone magnetometer location may not have been perfectly accurate, and this would cause a change in the calculations, and distance would also change. Nearby metal sources could distort the magnetic field, especially, for example, like a lamppost or maybe screws in the table as well. And just like human error in measuring specific values or inconsistent phone handling, since the measurements for distances were so specific. So for the supplemental questions, what if you hadn't orientated your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle? So magnetic fields would change because the magnetic force would not be correct as far as the magnetic north specifically, and both x and y components of the vector would obviously change. And then what if you were to stick 2 identical magnets together end to end? The magnitude of the magnetic field would be greater due to the combined magnetic fields, And the physics principle suggests that would be by a factor of 2. And then the measured distance would also decrease as magnetic fields are stronger. Thank you.